Okay, so the diagram shows faces of two ammeters. One is analog and the other is digital. What is meant by the terms analog and digital? So analog is described as continuously varying, so it can take any value. So there's nothing to stop it reading, 3.05, even though that's in between the divisions on the meter. Whereas a digital can only take preset values. It is not capable, for example, of taking the value of 3.145. It would have to round that up to 3.15. So it says name the components from which logic gates are made. So the device is called a transistor. Pretty much every electrical device known to man uses transistors, but it would also have some other components in it too, like resistors, diodes, etc., depending on the device. Okay, so in the space below, draw the symbol for an AND gate and label inputs and output. So that is our AND gate. Inputs are A and B, output is the one labeled Z. Describe the action of an AND gate. So if both inputs are high, the output is high. Otherwise, in any other situation, the output will be low. So draw a symbol for an OR gate. So there's our OR gate. Again, our inputs are A and B, and our output is Z. In terms of describing an OR gate, this time, if either of the inputs is high, the output will be high. Doesn't matter if it's just one or both. If both inputs, however, are low, the output will be low. So in 3 scenarios, it will be high, and in 1 scenario, it will be low. So the diagram shows part of a low voltage lighting circuit containing 5 identical lamps. Complete the circuit by the addition of components as necessary so that the total current from the supply can be measured. So we're going to need some sort of ammeter in our circuit. So there's our ammeter connected to the supply. We can put it before or after, it doesn't matter. So we want to be able to vary the brightness of lamp E. So I'm going to put a variable resistor in series, and by changing its resistance, we'll change the potential difference across E, so we'll change its brightness. C and D may be switched on or off together, whilst A, B and E remain on. So we've put the switch there, so it essentially allows or stops the current going through C or D, but has no effect on A, B or E. All 5 lamps are marked 12 volts, 36 watts. Assume that the resistance of each lamp is the same, fixed value regardless of how it is connected in the circuit. Calculate the current in one lamp at normal brightness. So I'm going to use P equals IV. We've got P, we've got V, so we can calculate the current is 3 amps. The resistance, so we've got potential difference and we've got current, so now we can calculate resistance using V over I, and it's 4 ohms. The combined resistance of 2 lamps connected in parallel with a 12 volt supply. So if they're in parallel, we need to use our reciprocal rule. Both of them are identical, so they're both a quarter, so we end up with resistance equals 2 ohms. We've got half of them essentially. The energy used by a lamp in 30 seconds, I'm going to use E equals PT. We know the power, we know the time, so we can calculate what the energy is. The whole circuit is switched on. Explain why the brightness of lamps A and B is much less than one of lamp operating at normal brightness. Well, I think there are 2 reasons. So they're connected in series, which means there's going to be double the resistance in their section of circuit. So the current is going to halve through the light bulbs. The other thing is that as they're in series, the potential difference is shared. Because they're identical, so it's shared equally. So putting those 2 together, I and V are both halved, so actually power gets quartered, and that's why the brightness is going to decrease quite a bit. Okay, so we've got the plan of a small apartment. We've got 2 60-watt bulbs in a living room, 100 watt in the kitchen and 100 watt in the bathroom. Power for the lamps is 200 volts AC, and the lamps are all in parallel, so all of them parallel, 4 light bulbs total. Draw a lighting circuit diagram so that 1 switch for each room and 1 master switch to turn them all off. Okay, so Here we go. The master switch is the one that's in series with the AC power source. We've got the two living room in parallel with each other with one switch to control both. Then we've got the bathroom, and then finally we've got the kitchen, each on separate circuits. The 100-watt lamp is switched on. Calculate the current. So P equals IV. We know what V is because it's the same across all of them. It's 100. We now know, sorry, 200 even. We know what the power is, so we can get the current. And once we've got the current, we can calculate the charge by multiplying it by the time. And we can see that comes out as 30 coulombs, so actually a lot of charge. So 3 60-watt lamps are replaced with 3 energy-saving ones, same light output, but each are rated at only 15 watts. So what that means is they're just much more efficient. So calculate the total reduction in power. So each one saves 45 watts, so 3 times that is 135. Calculate the energy saved when the lamps are lit for 1 hour. We've got E equals PT, so we do power times time in seconds, so we get our value for energy, and I would actually express that in kilojoules because it's so big, 48.6. Okay, so the next question wants us to draw a symbol for a NOR gate. So there it is. It looks like an OR gate, but it's got that circle on the front of it. That's what makes it a NOR gate. So we've got the inputs A and B, and the output is Q. There's no reason for choosing these letters, by the way. These are just pictures I found on the internet. So describe the action of a NOR gate in terms of its inputs and outputs. So if both inputs are low, then its output is high, but in all other situations, its output will be low. So it's exactly the opposite of an OR gate. So a chemical process requires heating at low pressure to work correctly. So when the heater is working, the output of a temperature sensor is high, or 1. When the pressure is low, the pressure sensor has a low output. If both outputs are fed into a NOR gate, a high output from the gate switches on an indicator lamp. So explain why the indicator lamp is off when it's correct. So if a NOR gate has inputs of 1 and 0, its output is 0, and so the lamp is going to be off. So state whether the lamp is on or off in the following situations. Pressure is low, that means its input is 0. Heater has stopped working, that input is 0. So we've got 2 0 inputs, so there's an output of 1, so it's going to be on. The heater is working, that means there's an input of 1, so we don't need to think about anything else, that's going to be off. So the diagram shows an AC supply connected in series to a diode and a resistor. On the axes, draw a graph showing the variation of the current in the resistor. So because we've got the diode, it's going to chop off any current going in the negative direction, if you like. So we're going to get a graph that looks like this, and the diode has essentially rectified or filtered out the negative section. So we've got 4 attempts to connect a circuit known as a bridge rectifier, or sometimes known as a full wave bridge rectifier actually. So the circuit is connected to a 12-volt AC supply. So what I'm going to do is in each of these circuits I'm going to explain what's going to happen when the current is positive and when the current is negative. So with A, if the current is positive, we're going to have the current going this way. So it's going to go through the diode, which is described as being forward biased because it's in the right direction. Once it's gone through that diode, it's going to go through the resistor because it can't go through the diode. So that's the path it would take. If it goes in a negative direction, we can see it's going to take this path. So you can see both directions have gone through the resistor. In this circuit, we can see the current would go in this direction here, and then when it's negative, it would also go in that direction. So it's going to go black to red in both scenarios. This next one, we can see it's not going to go through the resistor at all. It's going to go through 2 diodes and to ground without passing through a resistor, which it would do. Same thing for this circuit here. It's going to go through 2 diodes and to ground. It's not going to go through the resistor at all. And on this circuit, same situation. It's not going to go through the resistor. And same if we plot the other way, you can see it's not going to go through the resistor here either. So in which circuit will the direction of the conventional current always be from black to red? That was in circuit A. We saw it went from red to black. So on the circuit, you chose clearly indicate with arrows on the path of conventional current in the circuit when the upper terminal is positive with respect to the lower terminal. Okay, so I'm going to extend this on, so we've actually finished it off. So we said the top terminal is positive, so conventional current comes out of the positive terminal, follows this path through the resistor, and then all the way back to the power source. So that's the full path it would take. So the diagram shown uses a 12-volt battery. We've got two series resistors, but an open switch. So if the switch is open, state the reading on an ammeter. Well, it's going to be 0, because when a switch is open, resistance is infinite. The potential difference across S is going to be 12 volts, because one side of S is connected to the 12-volt side of the battery, the other side is connected to the 0-volt side of the battery, and there's no potential difference across either the 16 or the 8 because no current is flowing, so S is going to read 12. The switch is now closed. Calculate the current. So first of all, we need to work out the total resistance, 24. Once we've done that, we can use I equals V over R to figure out the current in the circuit. And then calculate the PD across the 8 ohm. Well, now we know the current, we can just multiply it by the resistance to get the potential difference. Or we could have used a potential divider equation if we wanted to. That would work too. So two resistors are now connected in parallel. Calculate the new reading on the ammeter when S is closed, stating clearly any equations that you use. So we've got them in parallel, so we need to use our reciprocal rule to calculate what the resistance is. And then once we've done that, we do V divided by R to get the new current, which is now much bigger because parallel resistors have a much lower resistance than series ones. So the diagram uses a 12-volt battery, and we've got two identical lamps, so they're both 18 ohms, each designed to work from a 6-volt supply. So the switch is open. State the value of the potential difference across S. It's going to be 12 because one side of it's connected to the 0-volt potential side of the battery, the other side is connected to the 12-volt side, and there's no potential difference across either A or B because there's no current, so it's got to be 12 volts. The voltmeter, however, is going to read 0 because there's no current, so there's no potential difference across A, so the potential stays the same, if you like, so the difference is 0. Comment on the brightness of the two lamps. Both lamps are going to be off because there's no current, so they can't be on. Switch S is now closed. State the new reading on the voltmeter. So the potential is going to split between the two, so there'll be a potential difference of 6 for one and 6 for the other. And comment on the brightness. Well, they're going to be equally bright, and they're going to be at their normal brightness because they're both designed to work at 6 volts. So they're basically operating under their normal conditions. So if each lamp has a resistance of 18, get the current. So the total resistance is 36. The total potential difference is 12, so we're going to get 12 over 36 gives us 0.33. With the switch S open, lamp B is connected in parallel with lamp A. With no current, each lamp has a resistance of 1.8 ohms. Calculate the combined resistance of A and B. So it says they're in parallel, so we're using our reciprocal rule to get their total resistance of 0.9. So just a quick thing, if you have two resistors in parallel and they're the same resistance, you always end up with half one of their resistances at the end. Stated why it would not be wise to close S when A and B are in parallel. Well, they're both designed to work at 6 volts, and if we put them in parallel, we're putting 12 volts across them. So either the filaments in them are going to melt, or if they have a fuse, that would blow to protect them. But either way, you're going to break something. So we've got two electrical circuits. So we've got 4 and 6 ohm resistors, one in series, one in parallel. But the batteries in the two circuits are the same. put ticks in the table to describe the connections. So P and Q in circuit 1 are clearly in series, and then circuit 2 they're in parallel. So resistors P and Q are used as small electrical heaters. State 2 advantages of connecting them like they are in circuit 2. So in parallel, if one heater breaks, the other can still work. That could be useful. The heaters can be controlled separately with separate switches. That could be useful. And actually, in parallel, they're going to run at higher power because each heater has a higher potential difference across it and a higher current going through it than compared to them in series. So that seems good. So the ammeter reads 1.2 in circuit 1. Calculate the reading on the voltmeter in the circuit. So essentially we need to add together the potential differences across the two resistors. So that's what I've done, times up by the current, and then we get our potential difference. The two switches in circuit 2 are closed. Calculate the combined resistance. So we're going to be using our reciprocal rule. We need to flip it back over and we can see we get 2.4 ohms. When the switches are closed in circuit 2, ammeter 1 reads 5 amps and ammeter 2 reads 2 amps. Calculate the current through P. Well, it's going to be 5 minus 2 gives you 3 amps. Get the power supplied to Q. I'm going to use P equals I squared R. We know the current, we know the resistance of Q, so we can get 24 watts. We could also use P equals IV or V squared over R. They should all give us the same value. The energy transferred in 300 seconds, well, energy is power times time, so that's a fairly straightforward calculation. So we've got an AND gate with inputs A, B and one output. State the output when A is high and B is low. It's low or 0. If A and B are both low, it's low as well. It's a regular AND gate. We can only have a high output if A and B are both high. So an electrical thermometer in a greenhouse gives a low output if the temperature is too low. The humidity sensor in the same greenhouse gives a high output if the humidity is too high. An alarm sounds when both the temperature is too low and the humidity is too high. Complete the diagram below to show how a NOT gate and an OR gate may be used to give the required output. So we want when the temperature is low to give a high output. So we're going to need a NOT gate for the thermometer because when the temperature is low, that output's 0, so we want that to then turn into a high input. And then we OR both of those, and both of those, so that when they're both at 1, the alarm goes off. So this is what we have. We have a low input to the NOT gate, so the output's high. We have a high input from the humidity sensor, and that gives us a high output from the AND gate. The diagram shows a car battery being charged from a 200 volt AC main supply. State the function of a diode. Well, it only allows current to flow in one direction, or we could say it's starting to rectify the AC is the technical term for what's happening. The average charging current is 2 amps and the battery takes 12 hours to charge fully. Calculate the charge the battery stores when fully charged. So we're doing Q equals IT and then we can do current times time. That gives us the total charge in coulombs, and I fundamentally hate this question because it implies when you're charging the battery you're pushing charges into it, which is exactly not what's happening when you're charging a battery. You're just reversing a chemical reaction, but this is how you're expected to answer this question, however fundamentally wrong it is. The battery has an electromotive force of 12 volts and when connected to into a circuit supplies energy to the circuit components. What does electromotive force of 12 volts mean? Well, it means each coulomb of charge that passes through the battery is given 12 joules of energy by the battery. So it increases its energy by 12 joules. In the space below, draw a circuit diagram to show how two 6-volt lamps should be connected to a 12-volt battery to be at normal brightness. Well, they have to be in series, so each gets 6 from a 12-volt battery. If the power of each lamp is 8, calculate the current. Well, I'm going to use P equals IV. If the power of 1 is 8, the potential difference is 6, we get 1.3 amps. Calculate the energy used by 2 lamps when they are lit for 1 hour. So we're doing it 2 times because we're doing it for both lamps. The power of 1 is 8, and we're doing it for 1 hour, so we're timesing it by 60 squared. That gives us our total energy in joules. Billy is building an electronic alarm. He wants a warning light to come on when it's light and a door is open. He tries this system. The light sensor gives a high output when it's light and a low output when it's dark. The door sensor gives a high output when the door is open and a low output when the door is closed. When will the warning light be on? So it's an AND gate, so they both need to be 1, so it's when it's light and the door is open. So the diagram for a light sensor is shown. Calculate the output voltage when the resistance of the LDR is 800 ohms. So there are 2 ways I think you can do this. You can use the potential divider equation to calculate it, or you can work out what the current is in your circuit using V over R, and then use V equals IR to find it. And you can see we still get 5 volts, and either method is absolutely fine. Describe how the resistance of the LDR changes when the light level increases. Well, its resistance decreases. Well, Billy wants to be able to trigger the alarm at a higher light level. Describe how the light sensor circuit can be changed to do this. Well, you change the fixed resistor for one of low resistance. So we're not changing the LDR, we're changing the other resistor. And if we do that, the resistance of the LDR would have to drop more before the potential difference reaches the high level. And if you want to see how that works, all I'm going to do is say we're still going to trigger it to high at the same voltage. So whatever the fixed resistor's resistance is, it's still going to trigger at 5. So what I've done is I'm finding what resistance the LDR would have to be in order to trigger it with now a new fixed resistance value of 500. And once I solve this, we can see that X is 400. So in this situation, the alarm would only be triggered when the LDR resistance reaches 400 ohms, whereas previously it was at 800 ohms. So you can see it's going to have to be much brighter, and actually twice as bright, for the alarm to be triggered in this case. Why is resistor R1 needed? We're looking more closely at the warning light circuit. We've got a resistor and a LED. So the resistor there is to essentially remove some or transfer some energy from the charges, and it's also going to reduce the current. So the input to the LED is going to be lower energy and lower current, so it's less likely to cause any damage by overheating. When the LED is on, it has a voltage of 1.4 volts across it and a current of 10 milliamps through it. Calculate the resistance of R. So first of all, we need to figure out what the potential difference is across the resistor. So it's going to be 5 minus 1.1. And then we divide that by the current, and that gives us the resistance. So you have to be very careful which potential difference you choose. James is designing a simple alarm. He wants an LED to come on when the light beam is broken. Here is part of the circuit. Okay. When the light beam is broken, the light level on the LDR falls. Explain how this affects the voltage across the variable resistor. So when it gets dark, LDR resistance increases, so circuit current decreases. And then using V equals IR, if current decreases, the voltage across the variable resistor decreases as well. Or we could use a potential divider argument here that would work equally well. So explain why the LED now lights up. Well, if the voltage entering the NOT gate is now low because it's decreased, the NOT gate output's high, and that's going to turn the LED on. Explain why James uses a variable resistor. Well, that's going to allow him to change the light level that triggers the LED to be changed or to be varied, so he can change the settings on it essentially. So John has drawn a part of an electronic system which he hopes will control a security light on his house. We've got a heat sensor and a light sensor going into an AND gate into a relay, and that relay can activate a security light. Describe the conditions which make the security light come on. Well, if it's hot and light, those inputs are both going to be high. That activates the relay, that activates the security light. John wants the security light to come on when it's dark and body heat is detected. To do this, an electronic gate must be added to the system. Draw the symbol for the gate in the correct place on the diagram. So we want the light sensor to be knotted because we want dark to activate it. So when it's dark, the light sensor outputs 0, so the NOT gate outputs 1. So that's our change. What's the purpose of a relay? A relay allows a low power circuit to activate a high power one, and that protects our components so our logic gates are low power components. We can't have high currents going through them. So the diagram shows a similar circuit used in a warehouse to activate a security alarm when it is dark and movement is detected. The resistance of the movement sensor goes high if movement is detected. Okay. The level of darkness needed to trigger the alarm is set by a variable resistor, which we can see on the top left. Circle it. Well, there it is. The value of the variable resistor is increased. Explain how this will affect the light level at which the alarm is triggered. Okay, so a larger variable resistor value increases the potential difference across the resistor and therefore decreases the voltage at the AND gate. Okay, so it's going to have to be much darker before the voltage at the AND gate increases enough that it crosses the threshold and it actually activates the AND gate in the circuit. So to trigger the alarm, the potential difference across the LDR must be 3 volts or greater. The LDR has a resistance of 400 ohms. The variable resistor is adjusted and slowly until the alarm is triggered. Calculate the resistance of the variable resistor when the alarm is triggered. You must show you're working out. So I'm going to use the potential divider here. So we know the potential difference across the LDR is 3. And we know the resistance of the LDR is 400, and we know the total potential difference is 9. It shows us on the diagram. So all we need to do is rearrange that and solve R. And we can see it's 800, which we actually could have predicted because we can see that 1/3 of the potential differences is across the LDR, so 2/3 must be across the fixed resistor. So that's kind of an intuitive one. Suggest why the alarm may not sound even if the potential difference exceeds 3 volts. Well, what if the motion sensor isn't activated? You can see it's an AND gate, so we need the movement sensor to be activated for the alarm to turn on. So if it isn't, then even if this goes to 3 volts, it's not going to turn on. And that completes this set of electricity questions.